Hello and welcome back to another release video of a memory board for the Sound Blaster AWE64. In my last video we have looked at the Minuet. This board is live, you can get the Gerber files on my website, there is also the bills of material, the video is already live if you haven't seen it, I'll link it in the top right corner. And you can also head over to PCBWay, order the PCBs and build one of these boards yourself if you want to. Today we are going to look at the bigger brother of the Minuet, the MIDI FORGE Sonata. This is a 28 megabyte board and it isn't 100% complete yet, but we are going to fix this today. This video is brought to you by PCBWay. More about them later. One big advantage of the Sonata is that you do not need a GAL chip. That means you don't need to flash a chip, you don't need any code, programming and so on. You just have to put off-the-shelf components on this PCB and you're good to go. What is still pending on this board we will get to in a moment, but first I need to revert back and talk a little bit about the first revision that I made for this board and how I ended up with this one. The MIDI FORGE Sonata uses 3.3 volt memory chips. These are 8 megabytes each and that is why we can get away with only 4 memory chips. The drawback is that these memory chips are 3.3 volts, but the Sound Blaster AWE64 has a 5 volt interface. So we shouldn't connect these memory chips directly to the sound card. And that is why we have these 4 chips here. These are level shifters. And these are all the same. I will put a model number on the screen that you know what type of chip this is. These level shifters allow one side to communicate with a sound card and the other side to communicate with a memory chip. So one side communicates with 3.3 volts while the other side is communicating at 5 volts. And this level shifter is building a barrier that no 5 volt signal is reaching the memory chips. And also in the other direction, the memory chips are only communicating with 3.3 volts. This level shifter will send a 5 volt signal to the sound card. Now we also have to distinguish between different signals. There are unidirectional signals, for instance the memory address. Memory addresses are only sent from the sound card, from the memory controller to be precise, to the memory chips. Other unidirectional signals are for instance the CAS and RAS line, but you have also the output enable or the write enable signal, or any other signal that is used to control the memory chips. Then we have bidirectional signals. These are the data lines. The data lines communicate in both directions. When we write to the memory chip, we send information from the memory controller to the memory chips, and when we read, we send information from the memory chip to the memory controller. And this is where I had most problems to get this to work. Initially, I used 4 identical level shifters. These level shifters have a direction pin, which controls in which direction the data is flowing. Now for the memory address lines, this is very easy. We always go from the sound card to the memory chips. The problem are the data lines, and this is where these 2 level shifters are connected to and have all these extra wires connected to. I have to control for every read and write signal the correct direction for these 2 level shifters. And there is no single signal that comes from the sound card that I can just use to control these 2 level shifters. Believe it or not, this board almost worked. Almost. We'll go over to DaVinci Resolve now and analyze what sound output we get with this board. And we will compare it to one of the other boards that I designed, specifically the Symphony, because this is built after Creative's memory board and should give us a good baseline what to expect from a board. And then we can verify if our memory board works correctly. Okay, now we are in DaVinci Resolve. I have 2 audio tracks. One is for the Symphony and the other one is the Sonata. So this is our reference audio track that's selected right now. And the Sonata is the new one. Now let me mute the Sonata and let's listen to our Symphony board. Okay, that sounded pretty normal. Now let's listen to the same on the Sonata. It did sound similar. I'm not sure if you can hear it. It probably depends on the compression on YouTube. It depends on your headphones. But the Sonata did sound a little bit off. And there is one specific part of that track. I think it's somewhere here. Let me find it quickly. Actually, it's exactly this. Now listen to the Sonata. Did you hear the noise after the loud note? This isn't there on the symphony. So let's drop a frequency analyzer here. I already picked it. So here are our two analyzer windows. One is for the symphony and one is for the Sonata. Let's see how these frequencies look like. And we can play these even without having to listen to it. I think this is through the entire soundtrack. So you see that around, what is this, 20,000 K? Maybe a little bit higher or lower, I'm not sure. But anyway, you see that here we just get that curve that goes down. But here at the end, we remain high. Here it's very visible. So yeah, there's extra noise. I don't know why it's there, but it must be because of the switching of the level shifters. I'm not an expert, but I didn't expect such an outcome from a memory board when this is clipped to the sound card, but it did. And yeah, so I had to come up with a different solution. And from my research working on the 16-pin SIM modules and talking to way more experienced people than I am, I came across the LSF0108. It is a level shifter that doesn't have a directional pin. It basically relies on the communication between two devices to determine in which direction it should switch. It is a lot easier to implement because you do not need to care about the directional pin. But in this case, we do need more components, specifically pull-up resistors for the 5-volt line. And this is what we are going to do today. We will figure out which values we need to have on our pull-up resistors to make this memory board work. I thought it's an interesting way of introducing this board to you if you decide to make one of these boards yourself or you get them through me later on. You do know what's going on these boards. So what have I done so far? I used values mentioned in the datasheets and I used 330 ohm pull-up resistors, but they seem to be way too strong and the board didn't work at all. Then I used 1 kilo ohm resistors and yeah, it detected the memory, but it was still not usable. The only other resistor arrays I had were 2.7 kilo ohms and they work. So this board is completely working. However, when I look at the signals with an oscilloscope, I can see these tiny spikes and they are not really nice signals. So the pull-up resistors are responsible that after the signal leaves the memory chip and goes through the level shifter, that we get a 5-volt signal to our sound card. So we should reduce the resistance of these pull-up resistors, making them stronger, so to say. They then allow more current to flow to our sound card, but that also means that our signal can rise quicker. And this is the entire goal, what I want to achieve today. I want to figure out if I can get a better signal to the sound card. But first, let's have a look at the symphony board, because there we can see how the signal should look like. If we look at the signal from the Sonata, you can see that the rising edge of our signal is somehow curved. And this is because the pull-up resistor is not strong enough to get enough current onto the line. Now, if we compare this to the symphony, you will not see this arch at the rising edge of the signal. And this is because the data comes directly from the memory chip. There's always one memory chip active on this memory board at any given time. And that is why the signal comes in as clean as it is here. But on the Sonata, the level shifter is in between and we need the pull-up resistor. What I want to do now is to put back the 1 kilo ohm resistor, because I know this is definitely not working. However, I would like to see how the signal looks like when we have a pull-up resistor that is too strong. All this fiddling with PCBs wouldn't be possible without today's video sponsor, PCBWay. PCBWay is my go-to destination for printed circuit boards. They are cost-effective, they have a very quick turnaround time, and the quality is always top-notch. They can also help you with CNC machining, 3D printing, sheet metal fabrication, and injection molding. And if you haven't signed up with PCBWay yet, now is the best time. PCBWay celebrates their 11th year anniversary. There are exclusive coupons up for grabs, special offers for PCB orders and PCB assembly, and you can win amazing prizes. Don't miss this opportunity and head over to PCBWay.com. And the MIDI FORGE Sonata will be on PCBWay's shared project space. Now you have another reason to visit PCBWay.com and see what they have to offer. Links are in the video description. Okay, and we are under the microscope. Here you can see our LSF0108. This level shifter doesn't have a directional pin. And this one here is the NH245. I'll put the full model number on the screen. This is for our address lines. So this is for the address line, this is for the address lines, and here is another LSF0108. This is data, and this is data. Now these two are our pull-up resistors, and these two are our pull-up resistors. So now let me change this back to 1 kilo ohm. I already know that this doesn't work, but I didn't measure the signal at that time. So last time I did this, Unisound, the driver in DOS, did detect the 28 megabytes, but the moment I started the creative diagnostic application, it failed. So I'll use my hot air station to get these resistors off, and then we can try with 1 kilo ohm. Okay, 1 kilo ohm. Let's see Unisound. And the DRAM is not detected at all. It just skipped it. It didn't even bother. Okay, that's interesting. I think I got something else the first time I tried this. Let's try this one more time and see if we get a different result. Detecting DRAM. No. No DRAM being detected. Okay, so that's a little bit different from what I have had before. Let's quickly check what's going on with the signal. So the signal does look very similar to the 2.7 kilo ohms. I have to admit this, but I may not have the proper equipment, not the right experience. But yeah, so 1 kilo ohm is definitely too strong. We still see that the rising edge has the arch on the top of the signal. So, I can only imagine that when there are short signals coming right after each other, that there is not enough time to drain the line from high to low. Anyway, let me change now to 1.5 kilo ohms and let's see if the diagnose application is going to detect the memory. So 1.5 kilo ohms. Let's see if the diagnose application is going to detect the memory now. Okay, Unisound still detects it. Oh, we haven't seen this before. Whoops. That's not correct. I don't think, yeah, okay. Okay, 1.5 kilo ohms, also too strong. Okay, let's try 2.0. I can't believe 2.7 is maybe not as bad as I thought. I have a good feeling that 2 kilo ohms is a good value. This is what we need. Okay, 2 kilo ohms. And how much do we get? 28. There we go. 28 megabytes. Let's see if we get a successful test. And our test passed successfully. Now let's just see if we can play back some of the all synthesized music, because that is actually using the memory module. Yes. Okay, the memory module is working now with 2 kilo ohms for the pull-up resistors. I'll record this entire part now, because we will see what the noise level is for this memory module. At 2 kilo ohms, the memory module works. However, I didn't see any improvement in the signal, and we still get the round corners for the signals on the rising edge, at least for some of them. So I'm not really sure why this is happening. Why doesn't it happen for all of them? Sometimes there are signals that look perfectly fine, but others don't look as nice. So yeah, maybe you can let me know what is going on here. And what value for the pull-up resistors do you think is the best one for this memory board? 2 kilo ohms is very close to a value that didn't work, the 1.5 kilo ohms. But 2.7 kilo ohms gives a good margin. So yeah, I will go now full circle. I will go back and put the 2.7 kilo ohms back on the board, and that will be the final value I'll go with. Of course, I know many of my viewers have a lot more experience in electronics. Please let me know what you think, what value I should use, but I'm pretty confident that this should work well. Now, of course, I want to go into Windows and let's try Doom with a larger sound font. In my previous video, we have seen sound fonts up to 12 megabytes. Now with 28 megabytes, we can load much larger sound fonts. It's basically the best that you could get for the AWE64. Oh, 28 megabytes. Very nice. Okay, so if you've seen my previous video, 8 megabytes was the maximum we could put on our Sound Blaster AWE value with a Minuet memory expansion board. But now with the Sonata, we get 28 megabytes on our value edition. Then let's hear some of these larger sound fonts in Doom. 29.3. Okay, this one would actually fit. Let's see if we can get that masterpiece on there. Only 341 kilobytes left. Wow, the memory is full. Okay, I'm really curious how Doom sounds now. Okay, that wasn't bad, but I think I prefer the 12 megabyte sound font. That's of course very subjective. You can let me know in the comments which one you prefer from the three you heard just now. So this was the masterpiece. 29.7, let me just double check. 29.360. No, this is too large. This will not fit, surprisingly. Okay, let's see if we get another one that's close to 29. Let's try the general user 1.35. This one seems to be fitting in it. This will be the smallest sound font that we loaded today, but maybe the sound font is really good. Gus Live. Let's see how this one sounds like. And we have still 12 megabytes left over. Nice. Ooh, this is tough. I have a feeling that the best sound fonts are really around 8 and 12 megabytes. And this is also what many of you mentioned in the comments under my last video. Most likely games were optimized to use smaller sound fonts. So even though you have 28 megabytes on your sound card, you may not need to upload larger sound fonts. However, it's very subjective, it probably depends on the game. Doom definitely doesn't seem like it sounds much better or better at all when using larger sound fonts. For me personally, I think the best one is the Chaos 12 megabyte. This is the one that I like the most. But yeah, maybe you have some favorite sound fonts for Doom or for any other game. If you do, mention it in the comments for other people to try it out. The Minuet arrived. The final revision. Revision 2.1. This will be the final version. This is the one that you get at PCBWay.com. I'll build one of these and then we'll have a look. But I got more PCBs. Yeah, bigger box. The star of this video, the Sonata Revision 2.0. Also in the final revision, 28 megabytes in black and updated silkscreen. I will also build one of those. All in silver because it's just solder. But I think this looks nice as well. Of course you can get it in gold if you want to, but I think this is also a nice touch. But I'm really excited about... We have the Rhapsody in white. So this is going to be a new attempt. And by the way, this is gold. I got, again, a bunch of PCBs, and this is just because of economy of scale. And by the way, this board is going to be available at PCBWay's shared project space. So yeah, we have two launches today. We have the MIDI FORGE Sonata as well as the Rhapsody board. Both of them are available. And here is one of these boards. Now you see the golden color. So I'll build one of these as well. And let me know about the new updated design of this board. Do you like the new font style and how I placed it around instead of, well, what it was before? You can let me know which one you prefer. And here they are. The Rhapsody, the Sonata, and the Minuet. The PCBs are available at PCBWay.com. Go to their shared project space. Of course, I have links in the video description. So yeah, this is the Rhapsody in white this time. But I received feedback that overwhelmingly people prefer the matte black with a yellow silk screen. So the Rhapsody, which I haven't covered yet, is also going to be released today. Then we have the MIDI FORGE Sonata. So this is the final edition as well. This has the 2.7 kilo ohm pull-up resistors. And finally the Minuet. I already made a video about this one. 8 megabytes on the value, 12 megabytes on the gold edition. This is an option for you if you do not need 28 megabytes and you're looking for a DIY project. If you do want to get one of these boards through me, please check the video description. There is a link for each of those boards leading to my website. There is a dedicated blog post for each of those boards and the information what I need from you. And then you can get one of these boards fully assembled and tested to your location. And by the way, if you're curious, I checked the noise level of this board and it is exactly like the MIDI FORGE Symphony. So there is no extra noise at the end. I had to replace the level shifters for the data lines, and the one I'm using now, the LSF0108, seems to be working very well. I want to thank PCBWay for sponsoring this video. Without them, all of this wouldn't be possible. And of course, I'll also thank all my Patreons that are supporting my work and this channel. If you want to become a Patreon member, head over to Patreon and pick one of the membership tiers. Otherwise, you can just like this video or subscribe if you haven't already done so. And as usual, let me know in the comments what you think about this project. Until now, you have seen two boards, the MIDI FORGE Minuet, 8 megabytes, and the one from today, the MIDI FORGE Sonata. Let me know which one is your favorite, and maybe by the time I cut this video, I will get the updated boards. Then you also see a new version. It is black with white silk screen. Let's see if it arrives in time. I don't know. At the moment of recording, I don't have it yet. It's in the mail, but maybe I will have it and you will just see it here on screen. Let's wrap up. Thank you so much for your time. Thanks for watching, and I will see you in the next video. Take care and bye bye.